Hi, let's solve a related rates problem step by step. These problems are always follow the same type of process, so hopefully once we do this problem today, it'll make a lot more sense and make your related rates problems a lot easier. So let's get right into it. A 10-foot ladder is leaning against the wall. The bottom is sliding away from the wall at 2 feet per second. We want to know how fast the top of the ladder is falling down when the bottom is 6 feet from the wall. So first things first, let's draw it. With related rates problems and any word problems, we want to try to visualize it, make it a lot easier to see. So we're going to draw a wall right here. And then I'm going to make the ladder blue just for fun. Awesome. And we know that it is falling down. And this is the ground. All right, so step one is to define our variables. So let x be the distance from the wall to the bottom of the ladder. So we're going to say this right here is x. And we're going to have y be the height of the ladder on the wall. So y is the distance from the ladder to there, and x is the distance between wall and ladder. And x and y change with respect to time. So with related rates, you want to always relate the problem to a simpler or a different type of equation that you have used before. So immediately I see that this problem creates a triangle with the wall and the ladder. So I'm going to write a function, and that is step two. Step two is write an equation. Oops. Equation. So I'm gonna make it in red. So because I can see that this right here is a triangle, right? I'm gonna relate this to the Pythagorean theorem. So x squared plus y squared is equal to something, and the ladder stays 10 feet long, so we know that the Pythagorean theorem would be 10 squared, right, which is equal to 100, right? Because yeah, 10-foot ladder, so we know that this is 10. All right, so x squared plus y squared is equal to 10 squared. All right, step three, let's identify our given information. So let me write that down. Oh my goodness. Sorry guys, this pen is kind of new. Identify the given. All right, so we know that the ladder is 10 feet, right? We are told that the bottom is sliding away from the wall at 2 feet per second. So we know that this right here is going 2 feet per second. And this is a velocity. And we know that velocity is a derivative of position. So, and actually, if you didn't know, here's kind of a good chart. You have position, you have velocity, and you have acceleration. So velocity is just the derivative of position, and acceleration is just the derivative of velocity. So if you're given a position, say x, and you want to go velocity, velocity would then just be dx dt, or the derivative, right? And if you want to do acceleration, we'll say velocity is v. This will just be dv dt, and that is a. So again, if you're given position, how we are with x, we can convert that to a velocity, a distance over time, to be v. So we are given again. So that's just an aside. So we are given that the bottom slides away from the wall at 2 feet per second. So what that looks like is we know dx dt is equal to 2. And we want to find how fast the top of the ladder is falling down. So we want to find dy dt, right? And we are evaluating when x is equal to 6. All right, so that's all the information we have and all the information we want to know. So let's go to step 4. And that is to differentiate. So let's go back to our equation right here. We have x squared plus y squared is equal to 100. Let's take the derivative of both sides. So we have 2x times dx dt plus 2y times dy dt is equal to 0. And again, whenever you take the derivative of something like here, you always multiply it by d times the variable of which you are taking the derivative over d times the variable, or d, the variable with respect to that you are taking the derivative. So in this case, we are looking for time, right? We want to know how fast time. So the derivative with respect to is t, and the derivative taken varies. So for the x squared, the derivative the variable taken is x, and for y squared, the d variable taken is y. So that's how you get these dx, dt, dy, dt. All right, now that we have differentiated the equation, we go on to step 5, which is find y at x is equal to 6. So step 5 is solve. All right, so now that we have the equation, 2x dx dt plus 2y dy dt is equal to 0, we plug in our x because we know, we know that x is equal to 6 here, right? Yeah, we want to know when the bottom is 6 feet away. So let's plug in 6. So we have, and we plugging in. So before we plug into these equation, we need to plug into the original equation so that we find y as well. Because we know x, we don't know y, and we're trying to find dy dt. And we also know dx dt. So the only variable missing is y. So to find y, I'm going to write it here. We have x squared plus y squared is equal to 0. We know x is 6. Sorry, 100, not 0. And then now let's rearrange everything. So this becomes 36 plus y squared is equal to 100. Y squared is equal to 64. And that gets you y is equal to 8. All right. So now that we know what y, the position of y, when the position of x, or at the position of x is equal to 6, we can go back to this part right here and solve for the unknown, dy dt. So let's plug everything in. So we have 2 times 6 times dx dt, which we know is 2, so times 2, plus 2, we just found y to be 8, times dy dt, all of that is equal to 0. So now let's solve for dy dt. So we have 24 plus 16 dy dt is equal to 0. And from this we get dy dt is equal to negative 24 over 16 is equal to negative 3 over 2 feet per second. And that is your final answer. So what that actually means is that whenever this ladder is falling down, so it'll be something like this at this point, right? Whenever x is 6 at this new length and y we found to be 8, because the system is moving, the rate at which is moving is negative 3/2 feet per second. And there you go. Hopefully that helps with related rates, and I'll see you next time.